Welcome to this presentation. My name is Daniel Vogt, and I'm going to talk about wrist angle measurements using soft sensors. So the motivation of this project is that in the last decades, electronic devices have become more powerful and more portable, but the way we interact with them, the human-machine interface, hasn't changed much. We mostly use keyboards, computer mice, or joysticks. Even the Google Glass, which represents the near future of wearable electronics, still requires the use of a hand to go through the menus. So the question would be, what is the future of human-machine interfaces? And one way to go could be natural user interfaces, where the interface is designed to be as natural as possible to the user and creates a seamless interaction between the human and the machine. And this could be done, for example, by sensing movements around the wrist. But how could we do this technically? One way would be to use vision. We could place markers on the hand and have cameras around to sense the motion. This is very precise, but then you are limited to the room in which you are doing the experiment. To go outside, one could use IMUs, like the Prior VR. It will work outside, but then it can suffer from drift integration with time. Finally, one could use goniometers. It will be precise. It will give reliable absolute positioning, but they are mostly made of hard elements which wouldn't be comfortable to wear. So the goal here is to create a novel sensing wristband using soft sensors that allow easy interaction with electronic devices in any kind of environment. What we want to sense is the different degrees of freedom of the wrist, so the flexion extension, the ulnar and radial deviation, as well as the pronation and supination. We want the sensor to be low profile, comfortable to wear, and intuitive to use. The applications could be, for example, to control an MP3 player, a remote control. It could be to control robots, telerobotics, or also be used in video games. So to do sensing on the wrist, we'll place sensors in a similar way that we would place strain gauges on a rod. We want to measure 3 degrees of freedom, so we need 3 sensors. But there are additional difficulties when you want to apply this principle on the wrist. First of all, the skin is very stretchable. We need some sensors that can follow that stretchability. They need to be hyperelastic. Secondly, the shape of the wrist is not as simple as a rod. Especially there's an increase of circumference at the transition between the forearm and the hand. So if you place the sensors like this, the sensor A would see a lot of crosstalk if I do the movement flexion extension, and ideally I wouldn't want to see anything on that sensor. So the ideal positioning of the sensors would rather look like this, where sensor A and B would be on the top of the wrist, and the sum of the readings will give information on the flexion extension, when the difference of the readings will give information on the radial deviations. Finally, the sensor C here will only measure the pronation and supination of the wrist. A few words on the fabrication. How we fabricate these soft sensors. We use molds that are 3D printed. One mold is flat. The other one contains a design of microchannels. We pour very low stiffness silicone rubber on it, and then spin coat the flat layer to then bond the top layer containing the microchannels. Once everything is bonded together, we inject a conductive liquid, which is E-gain. It's a metal that is liquid at room temperature. And so we inject this liquid metal using syringes, one syringe to inject the liquid, and the other one to take the air out of the microchannels. And then we can plunge the wires and read this like any kind of strain gauge. Here's what it looks like in action. There should be a video on the right. But what happens is that when you apply strain on the sensor, the overall length of the microchannel will increase and the cross-section will decrease. And both of these actions will result in increasing the electrical resistance. I'll see if I can play this video. So it's not exactly the sensor being used, but it's exactly this. It has been fabricated in the same manner, and here you can really see how stretchable these sensors are. The material itself can be stretchable up to 900% before it breaks. Then we have to place the sensors on the wrist. And for this we use rubber straps. These rubber straps are made from the same material as the sensors. They provide the good quality to not slip, to barely slip on the skin surface, which is really essential here. And we fix the sensors using Velcro. And this should be a video here also not working. But the way we fabricate these rubber straps is that we pour this elastomer and use a squeegee to get a very flat surface. And then we use a laser cutter here to cut the outline. I'll just skip these videos. Then we need a way to compare the values from the soft sensor with the actual angular values. And for this, we designed this calibration device on which we can put the arm, and then it will capture all the rotational movements of the wrist without moving the forearm. There are potentiometers in every of these pivot links. And also something important about this device is that we can lock every of these pivot linkage to measure just 1 degree of freedom at the time. That's very important. And here's what the results look like. So for flexion extension, you can see that sensor A and B in red and green sense most of the movement and in a similar manner. Opposed to the ulnar and radial deviation, where it's also sensor A and B that sense the movement, but this time in a differential way. When the sensor A is stretched, for example, the sensor B is contracted. And for pronation and supination, it's mostly sensor C in blue that sees what's happening. And then to convert the values from the signals into angle data, we are using a calibration matrix, mostly because it changes time to time when you place the sensors. You can apply different pre-constraints or place it in different manners, so we need to do a calibration every time. So from the slopes of the plots that I showed before, we report the slopes in a matrix that we invert using the Moore-Penrose method, and then we can get the angles from this formula. And if we compare the angles from the wrist sensor and the calibration device, it looks like this with the wrist sensor data in dashed, and we get the following errors. We can also do a blind calibration. This is interesting if you want to use this device outdoor without this calibration tool. It's a simplified calibration process where the user is asked to move sequentially its wrist into the maximum deflections, and the slopes are measured with only 2 points. And the output corresponds to an angle normalized to the maximum wrist deflection. For the rest, the maths are exactly the same. So a few examples of application. This is an example controlling a 3 degree of freedom servo motor on which we can place a camera or a gripper or whatever. And you can see how the angles of the wrist sensor, how they actuate this 3 degree of freedom servo motor. Something slightly more challenging but also more fun is with the sensor to control a quadcopter. In this case, the flexion and extension are controlling the yaw of the copter, the radial deviations are controlling the pitch, and the pronation supination are controlling the roll. You can see here all the signals involved doing this. At first, we gather the values from the wrist sensor. They are amplified. We use an Arduino to do the maths using the calibration matrix. It outputs a PWM that is converted to an analog signal using an RC filter. And then we input the analog value to a modified remote control that transmits wirelessly to the quadcopter. So this is all what I wanted to talk today. In summary, what is presented here is the design and characterization of a novel human-machine interface to measure wrist angle using soft sensors. The next step would be to have a better understanding of the skin deformation, to have a better knowledge of how to place the sensors in a more optimized way. What we can also do is to integrate this wrist sensing band with a watch. It's the ideal position for that, and this watch could contain the power source, but also do the signal conditioning and maybe even transmit the data wirelessly. That's all what I wanted to present today. Thank you for your attention.